Now let us move to the next illustration. In next illustration, 1 mole of an ideal monoatomic gas taken around the cyclic process A, B, C and A, right? And we need to calculate here the work done by gas. In second part of the question, we need to calculate the heat rejected or absorbed by the gas in the process C to A, and also we need to calculate the heat absorbed by the gas in the process B to C, right? And in the third part, we need to calculate the maximum temperature attained by the gas during the cycle. So, let us move to the first part, that is work done by the cyclic process. If you observe this process, this is a cyclic process on the PV diagram, and we know when we have the PV diagram, the work done is calculated by area under the curve. That means work done in this cyclic process is equal to area of this triangle, and we can observe here this cyclic process is a clockwise, and clockwise cyclic process always has the positive work done. So, we should have the positive work done in this cyclic process, and this cyclic process is a right angle triangle. That means this work done is equal to this side multiplication this side divided by 2. So, let us calculate the work done by the cycle equal to 1 by 2 3 P naught minus P naught and multiplication 2 V naught minus V naught, right. And this 3 P naught minus P naught is 2 P naught and 2 V naught minus V naught equal to V naught. So, this is equal to 1 by 2 P naught multiplication V naught, that is equal to P naught V naught. So, this is the work done in this cyclic process. Now, let us move to the next part of the question. Here we need to calculate heat rejected or absorbed by the gas in the process C2A. Okay. You can observe this C2A process is the isobaric process. First of all, let us decide whether heat is absorbed or it will be rejected. You can observe here in this process pressure is constant, and if pressure is constant, we know we have the ideal gas equation PV equal to nRT, right. And if this is constant value, that means V is proportional to T, and if V is proportional to T, that means if volume is decreasing, temperature of A point will be less than the temperature of C point, that means temperature will decrease. And we know heat associated with the any process, especially in case of the isobaric process, we can write QCA equal to N Cp multiplied by delta T, right. So, we can write this formula, and we know this temperature of A is less than the temperature of C, that means this value should be negative. If this value is negative, that means heat should be rejected, that means in this process heat will be rejected out. So, we can calculate now N here is equal to 1, because we are given 1 mole of an ideal monoatomic gases, and it is the monoatomic gas, that means Cp equal to 5 by 2 R, and temperature at this position, that is position A, is P naught V naught divided by R, because we have equation PV equal to nRT, that means T equal to PV divided by nR, and N is the number of the moles, that is equal to 1. That means temperature at position A is equal to P naught V naught divided by R, and temperature at this position equal to P naught 2 V naught divided by R. So, let us substitute these values here, and on solving we get this value equal to minus 5 by 2 P naught V naught, because negative sign is because of the heat is rejected by the system. Okay. Now, let us move to the next part of this section, that is the heat absorbed by the gas in process B to C, that means in this process. You can observe here this is isobaric process C to A, and A to B is the isochoric process, and this process is not categorized under any heading. That means we need to calculate the heat associated with this part BC by indirect method. So, in this process we need to calculate the heat associated with the BC process, and that can be calculated very easily by using the formula, because it is the isochoric process, and we can calculate the heat associated with this process by a direct formula, that is equal to N Cv multiplied by delta T. So, let us calculate the heat this equal to this. Why we have written absorb? Because temperature of this position is greater than temperature at this position. This is the isochoric process, and in isochoric process the pressure is proportional to T. If pressure increases, temperature will increase. That temperature of B is greater than temperature of A. That's why we have written heat absorbed in the process AB, right? Now, this is a monoatomic gas. That means this value is equal to 3 by 2R and N equal to 1, and this TB, that is the temperature at this position, equal to, this is 3 P naught V naught divided by R, and temperature at this position is equal to P naught V naught divided by R. So, let us substitute the values here, and on solving we get the value of heat absorbed in this process equal to 3 P naught V naught, right. Now, we have calculated the heat in this part and this part. In this part heat was rejected and this part heat is absorbed, right. And we know this is the cyclic process, and in any cyclic process heat supplied is equal to the work done by the gases, and work done by the gas we have calculated in the first part, that is equal to P naught V naught. That means we can write heat supplied equal to work done by gas, right. And heat supplied should be summation of heat associated with this part. This is equal to minus 5 by 2 P naught V naught, and heat associated with this part, that is equal to 3 P naught V naught, and we need to calculate heat associated with this. Then this is equal to unknown value, that is QBC, and that should be equal to total work done, that is equal to P naught V naught. So, let us substitute the value. Now, this part is only unknown value. So, this is equal to QBC is equal to, this is P naught V naught plus 5 by 2 P naught V naught minus 3 P naught V naught. So, let us calculate this value. Calculation, we will get the value. This is equal to P naught V naught divided by 2. So, heat supplied by the gas in this process equal to P naught V naught divided by 2. Okay. Now, let us move to the last part of this question, that is the maximum temperature attained by the gas during the cyclic process, right. We know the temperature at this position, at position this is equal to P naught 2 V naught divided by R, because N equal to 1. So, we are writing 1 multiplied by R, and here the temperature is equal to P naught V naught divided by 1 multiplication R, and here the temperature associated with the position B is equal to 3 P naught V naught divided by 1 multiplication R, right. That means temperature at this position will be highest in this process. Similarly, we can say temperature in this process will be greatest at this position. That means up to till now the temperature is highest at this position, but we do not know what will happen to the temperature from B to C. That means we need to investigate whether temperature at this process will be highest anywhere between the process B to C or not. For this purpose, what we need to do? We can write here PV equal to nRT, right. That means T equal to PV divided by NR. You know NR is constant. If multiplication of PV is greatest, T will also be the greatest. That means the temperature may be greatest somewhere between B to C. Okay. So, let us investigate this part, whether temperature is greatest in the process B to C or not. For this purpose, we need to write the equation of this straight line. You know, this straight line is having the negative slope and positive intercept, and the nature of the line is y equal to mx plus c type. So, we can write a general equation of this, because on the y axis we have written pressure, on the x axis we written volume. So, we can write this equation of BC equal to P equal to slope of this line multiplication V plus intercept. So, let us write this equation like this. This k is a slope and k dash is the intercept. We have the coordinate of point A, B and C. If we substitute the coordinate of B in this equation will become this one, because at this position B, the x coordinate or v coordinate is v naught and y coordinate or p coordinate is 3 p naught. So, this is equation number 1, you can say, and similarly we can substitute the value of coordinate C in this equation, and here the volume coordinate is 2 v naught and pressure coordinate is p naught. So, let us substitute this value. Now, we have the two equations and two unknowns, right. Now, we can solve. We have two equations. If we subtract, this will be minus, this will be also minus, they will get cancelled, and this is equal to 2 p naught, right, and here it is equal to minus k multiplication v naught. That means k is equal to minus 2 p naught divided by v naught. This is the slope of the straight line. That means we have calculated this value. Now, if we substitute this value in this equation or any of equation, we can get the value of k dash. So, on solving, we will have these two values. This is the value of k and this is the value of k dash. Okay, intercept is positive and slope is negative. Now, we can substitute the value of k and k dash in this equation. So, this is the pressure and volume relation for process BC, but we need to write the temperature relation, right, and temperature relation, for temperature relation we can use the ideal gas equation. We have the equation PV equal to nRT, that means P equal to nRT divided by V, and N equal to 1, that means P equal to RT divided by V, right. Now, we can write the temperature relation. If we multiply, cross multiply by V and divided by R, this temperature relation will become this one, that is T equal to P naught divided by R, and in bracket term 5 V minus 2 V square divided by V naught. That means the value of the temperature is depending on the volume. T is the dependent variable, V is the independent variable, and here we need to calculate the maximum temperature. For this, we can use the method of differentiation, especially maximum minima. For this purpose, we need to differentiate temperature with respect to volume and equate equal to 0, right, and differentiation of this term will become, because P naught divided by R is constant. So, in bracket term will be equal to, differentiation of this term will be equal to 5 minus 2 multiplication 2 V divided by V naught, and this is equal to, in bracket term will be equal to 5 minus 4 V divided by V naught. So, this is equal to T equal to, that is dt divided by dV equal to this one, and that is equal to 0. Now, we can further solve, because P naught divided by R cannot be 0, that means this term should be equal to 0, right. We can rearrange this term, and from this relation we can get the value of V equal to, this is 5 divided by 4 V naught, right. And let us find the value of T, whether temperature is maximum for this value or not. For this, we can differentiate this term again, that means double differentiation. So, on double differentiation, that means differentiating this term again, this is dt2 divided by d2v, this is equal to, in bracket term this will be 0, and this is equal to minus 4 divided by V naught, that means negative value. That means, for this volume the temperature will be maximum. Now, we can substitute the value of V in this equation, that is equation number 1. So, let us substitute this value, V equal to 5 V naught divided by 4. So, this is 5 multiplied by 5 V naught divided by 4 minus 2 multiplication 5 V naught divided by 4 whole square, and overall divided by V naught. So, let us substitute this value, this one, right. Now, we can solve. This is 25 V naught divided by 4, and this is again, you can observe here, this is 2, 4, 16, that is 25 divided by 8 V naught, right. So, this is final solving, value is equal to, this is 25 P naught V naught divided by 8 R. That means maximum value of the temperature during the process is 25 P naught V naught divided by 8R. Now let us move to the next illustration. Next illustration is again a cyclic process on TV diagram. According to the question, this cyclic process is defined as ABCA and it is performed on sample of the 2 mole of an ideal gas. That means number of the moles are 2. A total of 1200 joule of heat is withdrawn from the sample in the process. That means it is given heat is withdrawn from the sample. That means Q sign, the sign of Q, the sign of heat should be equal to minus. That means value of Q should be equal to minus 1200. If heat is added to the system, it should be substituted with the positive sign. If it is removed from the system, it should be substituted with the negative sign. So, Q equal to minus 1200 joule for the process. Okay. Now, the question is we need to calculate the work done by the gas during the part BC. BC is the curve path. We can define AB as a isobaric process. We can define CA as a isochoric process, but this curve path cannot be defined with any known process. That means we need to solve this problem by indirect method. Okay. So, let us move to the analysis part. You can observe here this is a cyclic process, and one very important concept about the cyclic process is the change in internal energy, that is delta U equal to 0. This is the very important property of the cyclic process. Okay. And we have the first law of thermodynamics. According to the first law of thermodynamics, the heat added to the system Q is equal to delta U plus W, right. You know, Q equal to heat added to the system and delta U is the change in internal energy, W is the work done by the gas, work done by the system. We can rearrange this equation, we can write W equal to Q minus delta U, right. And we know this Q according to the question, it is minus 1200 as we discussed. So, we can do one thing, we can substitute this value as minus 1200, and for the cyclic process we have discussed delta U equal to 0. So, this is equal to minus 1200 minus 0, that is equal to minus 1200 joule. That means the total work done in the process, in the cyclic process, equal to minus 1200 joule. You can observe here this is the counterclockwise cyclic process, and clockwise cyclic process always work done having the positive sign, and counterclockwise cyclic process work done always has the negative sign. So, it is having the minus 1200 joule, that is the total work done, right. Now, let us consider process one by one. This is the simplest process, CA. This is the isochoric process, and in isochoric process we know change in the volume delta V equal to 0, and if delta V equal to 0, that means there will be no work done in this process. So, here we can write WCA equal to 0, right. Now, if we consider the total process, the whole process, we can write WAB plus WBC plus WCA equal to total work done, that is equal to minus 1200, right. And we know this value WCA equal to 0, this is 0, that means WAB plus WBC equal to minus 1200 joule, and we can write this equation as equation number 1, right. So, write this equation as equation number 1 here, right. Now, let us consider the work done in this process, that is the AB process. AB process is the isobaric process, and in isobaric process calculation of the work done is a very simple one, that is equal to P delta V, right. And also we know in this process because pressure is constant, and we have this equation PV equal to nRT, and if this value is constant, then V is proportional to T. That means we can write here V is proportional to T for this process, right. Now, let us write the ideal gas equation again, that is PV equal to nRT, right, this equation. And we know work done equal to, because pressure is constant, work done equal to P delta V. We can place the delta sign on the both side, and if we place delta sign, this side will become P delta V and this side will become nR delta T, right? And we know this value, that is n equal to 2, here n equal to 2, r equal to 8.31, and delta T is equal to 500 minus 300, because final temperature is 500 and initial temperature in this process is 300. So, let us substitute this value, this one, right. If we solve this value will become 3324 joule, right, this value. That means work done in this process equal to 3324 joule. Now, reconsider this equation. Equation number 1, we have calculated WAB. If we substitute the value of WAB, this unknown value WBC can be calculated. So, let us substitute the given values, right. Now, we can calculate this value WBC equal to, if we solve, this value is equal to minus 4524 joule. So, this is the work done in BC process. Now, let us move to the next illustration. This illustration is again a cyclic process, but here the coordinates are internal energy and volume, right. And we are given 2 moles of an ideal gases for the cyclic process, and temperature at point B at this position, and temperature at this position are given as 500 Kelvin and 300 Kelvin respectively. And here we need to calculate the heat absorbed by the gas during this cyclic process. Okay. So, let us make the analysis first. First point, if you observe here, this is a cyclic process, and for the cyclic process we have delta U equal to 0, right. And we have another concept for this cyclic process, that is the first law of thermodynamics, that is Q equal to delta U plus W, right. And we know this value equal to 0, that means Q equal to W. That means, if we calculate the work done in the cyclic process, we can calculate the value of Q. Okay. So, let us move process one by one, and if we observe this process is an isothermal process, because internal energy is constant and internal energy is a function of temperature. That means, temperature constant means it is isothermal process, and isothermal process delta U equal to 0. Similarly, for this process we can observe again U is constant, and U is constant means temperature is constant. This process again isothermal process, and for this process we have delta U equal to 0, right. We can calculate the work done in this process and this process easily, because we have a ready-made formula for calculating the work done. We can write work done in isothermal process equal to W, and this W equal to nRT natural log V final divided by V initial, right. First of all, let us take AB process, this process. Here that is temperature equal to 500 Kelvin, right. And we can observe here the final volume is 2 V naught and initial volume is V naught. So, we can calculate WAB equal to nRT natural log 2 V naught divided by V naught, and this T equal to 500, right. So, this value is equal to 2 multiplied by R 500 natural log 2, that is equal to 1000 R natural log 2, right. Now, let us move to process CD, and from C to D volume is decreasing. If volume is decreasing, work done should be negative. Here we can write this work done equal to nRT natural log V divided by 2 V naught, right. And here the temperature equal to 300 Kelvin. So, this is equal to 2 R 300 multiplied by natural log 1 by 2, and this natural log 1 by 2 can be written as minus natural log 2. So, this after calculation will become minus 600 R natural log 2, right. Now, let us proceed to calculate work done in the process D to A and B to C, right. We can observe here the volume is not changing. That means, this process is isochoric process, and in isochoric process W equal to 0. And here we can again observe the volume is constant, again isochoric process, work done equal to 0. That means burden in these two processes is equal to 0, but there will be burden in this process as well as this process. Now, we can add the burden of all process to calculate the burden in complete cycle. So, W equal to WAB, this one WAB plus WBC, WCD plus WDA, right. And we know we have calculated the burden in WAB and WCD, this value and this value. Let us substitute these values here and here, and WDA equal to 0 and WBC is again 0. So, this is the summation of the burden. Now, we can solve this, we can add these values. This is 400 R natural log 2. That means the total burden in the complete cyclic process is this much, and we know in any cyclic process W equal to Q, that is the heat absorbed. So, this value will be also equal to the heat absorbed in the cyclic process. So, this should be the answer.